Okay.
You do you want the lab report in the video or separate?
We're going to talk about that. Give me a sec. Welcome back. We are GDD403. That's problem solving with data structures and algorithms in the winter 2023 semester at Canadore, and it's officially, it says week 3 here, but we're actually week 5 of our broadcast and recording together. And this week was all about sorting algorithms. And we're also going to do more in our in-class exercise today on that little card simulation thing that we've been talking about. In fact, that's going to be the main, little example that we're going to be using to help you with your assignment 1 as we go forward, get you guys all warmed up again with Unity and all those things, right? So as we go and continue what we're doing. All right, so again, this week's all around sorting algorithms. Just to look ahead, looks like we're into searching algorithms next week and a little bit of recursion, although we are going to touch upon that just a touch, like really a little bit today. Just as a head, does anyone remember what recursion means again? We talked about this really briefly. Recursion, what is it, and would you use it before we move on? If you don't know, you don't know. Just say you don't know.
Yeah, I forgot.
So recursion, it means that when we call a function from the function itself. So it's almost like a function that's self-calling, right? And why would we do something like that when it comes to data structures and algorithms in general? It's because the function becomes more quote unquote elegant in terms of the size of the function and what it looks like and so on. On the downside, it becomes a little bit more complex because when we look at it, we're like, how does this resolve? How do I stop this from looping? One problem with recursive algorithms, which we're going to see next week, is the danger of an infinite loop, right, is very real. And Stack Overflow, where the whole Stack Overflow site came from. It's the idea that we continue to call the function from itself. We make a copy of the function over and over again, and we put it on the stack, and then until we run out of memory. And so that's how kind of recursion works in general. It just kind of continues to loop forever. So that's we're going to talk about that, and it's kind of a way of doing it. Recursion. It's a way of looping without using while loops. Although anything you can do with recursion, we're going to talk about you can do with a while loop for the most part. Okay, so that's something that we're going to talk about next week. The week after that, as we look ahead, is your midterm test. We're into midterm tests, and it's clearly going to be on a couple of things we've talked about, which is getting GitHub, raising lists, sorting algorithms, searching algorithms, and anything we've talked about in class exercises are all fair game for your mid-semester tests. Again, the mid-semester test, the way we're going to run that is I'm going to release it early on in the week, Monday, and you'll have until Friday to get her done. Okay, that's how it's going to be. So it'll give you the entire week to work on it. It's not a timed exercise, or I'm going to watch you over your shoulder or have some weird, I don't know, thing in class, but it doesn't make sense. So I'll give you, it's almost like a week-long assignment. It's going to be worth, a chunk of marks, and your job is to basically, kind of do what I've asked you to do. It's going to be another example of something that we've talked about in class. Maybe it's something slightly changed, just to help you practice the same fundamentals before we get into the second half of semester, which is going to be more challenging because we're going to do other kinds of things with sorting and searching and data structures. Okay, so that's kind of the way we're doing it for the first half and the second half. Last week, what we did, we talked about arrays and lists really briefly. We also did in class exercise 2. We kind of created our Unity project in a more complete form. We added 3D cards to the project, and we also started our playing card simulation, which is part of your assignment 1. Okay, that's what we did last week. On that, I want to talk about assignment 1. I posted it, but I promised that I would do some kind of justice to it in terms of talking about what it's about. Let's do it now. So what is assignment 1? It's all around collections, which is more what I want you guys to do. So collections, and actually it's including other kinds of things in there. I always consider this kind of thing a warm-up assignment. And I mean that because it's only worth 8% of your final grade. And you're working with collections and classes and those kind of things in Unity. Again, I'm trying to make this as visual as possible, so it's not going to bore the crap out of you guys. Data structures and algorithms scientifically and academically can be quite boring. If all we do is focus on the actual algorithm or the code, and then you look at someone else's code, it's like, okay, and show me what this does. Like, I want to know how it works. And so that's why this exercise, this assignment is going to basically help you visualize what's going on, and then make it maybe a little bit more fun than what it is. It's a classic, the memory game or the matching game, where we have a series of cards, as an example, and you're going to match two. And that's how it's going to work. The way you're going to use the memory game is you're going to have a standard deck of cards. So now we have the card class from last week, and then we have a standard deck class. We're going to build that this week a little bit. And then some mechanical stuff we have to talk about today, which is going to be things like, how do I select? How do I do that with a mouse in Unity inside the scene when the scene is live? How do I do that? How do I highlight the thing that I'm selecting so it looks realistic? How do I add stuff like sounds and those kind of things so it makes the game a little bit more interesting? How do I activate and deactivate things from working and that kind of stuff? We're going to go all over that again as if you've never done Unity before. Okay, so if you've done Unity before and this is old hat for you, awesome. This is going to be a real easy part. If you haven't, if you forgot about Unity, or maybe you didn't go into such depth, great. You're going to get kind of more detail in terms of how to do all that stuff. The memory matching card game is not complex, but what it allows you to do is do things like, how do I compare two values? Like, I'm going to compare two cards. How do I do that? How do I shuffle a deck? How do I do that? How do I reset the deck, back to its original form? And that allows me to do things like, the shuffling algorithm that we're going to be talking about as well. In terms of sorting and searching, when it comes to values, if I'm going to sort and search values, we can do that. I'm going to search for a specific card. I can do that too. We can use this as an example of how to do that. But for the most part, what I want you more to do, which is kind of a little bit outside of sorting and searching, is get comfortable with the deck of cards in 3D. Use it as a vehicle for us to learn about collections and to use Unity a little bit, and to add a little bit more fun into the whole process. So that's what you're making. I've given you your assets that you can use. You can certainly use other ones. Let's say, for example, you really don't like my cards and you want to have cards that look like, I don't know, Game of Thrones or your favorite video game. I've been playing Dead Space over the last, since it's been released a little bit. Great remake. We'll talk about that a little bit today too, since we're all game devs, right? So we want to talk about some games, and Dead Space, great game. I don't know if you guys ever played it before, but it's a remake. I played it since it was released on the PlayStation way back in the day, and it's fantastic in terms of what EA has done. And I'm not a real EA fan, in terms of what they've come up with. It's a sad story what they did to the developer, right, of Dead Space, the original people that made Dead Space. Fantastic game, right? So, but going back to this, the idea is that you have a game, you're going to be working on something, and it's a little bit more applicable than randomly kind of coming up with assignments for data structures and algorithms. So what you're doing here is you're making the card class, which is what we did kind of last week for the most part. We almost did everything here. So if you follow along every week and you implement all the stuff we're talking about, it's almost like I'm helping you build your assignment. Now, there are going to be parts that you're going to have to do on your own. That's going to be just the way it is, right? I mean, that's what an assignment is, exploring how to do things and making all the final touches work and all that stuff. But for the most part, for this first assignment, I want you to get to know me, understand what I'm looking for, all that kind of stuff. I'll talk about, kind of layouts and all that. And so that all the mechanical stuff behind how to do an assignment, how to make it, kind of produce it and all that stuff will be completely finished. And then you'll know what I'm looking for from you. So this is kind of like, again, a little bit of a vehicle for me as well. So standard deck class is what we're going to work on a little bit today. And then there's Unity game requirements in terms of how you can make it work. So some things that we're going to have in the game is a difficulty setting. So, for example, you may have a matrix of cards that you're going to show, where you select the difficulty of easy, maybe it'll be a 2x4 card matrix, right? If it's 4x4, it'll be normal. As an example, 6x6 will be hard, and you can make other more challenging difficulty settings, an 8x8 or whatever it's going to be. The player can select an interface element and use a button to shuffle the deck. So it could be like some kind of button or some kind of keyboard, key combination to have the deck be shuffled, right? The cards are dealt, as an example, face down, so they're not going to be shown, right? That's how it's going to be. And the player then can select any two cards on the table with a mouse click. If the two cards match, an interface element, some kind of progress bar or score counter increments to provide feedback to the user. Okay, you got a match. You need 3 matches to win, as an example. And this could be almost like an infinite matching game, where you keep on matching until you're done, and then you can kind of add up, the maximum score that you've accumulated over the time, right? So that's kind of how it is. It's 3D, and we can also produce it on the web, so you can actually share this thing, like I said, with your, as part of your portfolio, if you wanted to do such a thing, right? So it's not a bad little app to practice with, and it can easily made into a mobile application as well. Okay, so we'll talk about that. So again, if the player matches all the pairs of the cards on the table, they have won the game, and a label appears that informs them. Now, one thing I didn't say is that you can make this game continue forever, and I'm going to give you that as an option. You can make, again, this is basic requirements that I've given you. You can extend this thing if you want to take it further, if you have time, and you may not have time between now and next weekend, but that's why I'm going to help you build some of these things together as we go forward. If the player fails to match, the game provides feedback the player failed to match, and the selected cards flip face down again. If the player fails to match 3 times, the game is over. So that's when you stop the game altogether. A user interface element and or button controls allow the player to reset the game. And what I wanted you to do is include impulse sounds for mouse clicks, successful match attempts, failed mouse attempts, deck shuffling, and other kinds of button clicks that you want to do to give feedback again to the user. Whenever we play a video game, sound is as important, if maybe it's even more important sometimes, than the actual stuff that we're seeing on the screen to give us feedback. Things that are also required outside of game requirements and code requirements are the following: some kind of internal documentation that includes your name, your student ID, your date, the date that you're making stuff, or you've updated it, and so on. Some other method and function headers is what I'm asking you to make. So something like, what does this function do, right? If you're going to make a function header, and we'll do a little bit of that today to show you what I'm looking for when it comes to coding style and that kind of stuff. Share your stuff on GitHub. We've talked about that, right? So I want you guys to put it up on GitHub. As always, and this is, again, some people are missing this with your in-class exercises, a video is required for your in-class exercises. So if you have not submitted a video, I will not mark your exercises going forward. Like I told you guys that last week. So please, if you haven't had a chance to review that, if you submitted an in-class exercise without a video, I may ask you to resubmit with a video, right? Video is your explanation of what the in-class exercise does. It's worth 4% of your final grade. It's not a small amount. So it is a video report is what you're making. There is a single slide. And I know that we asked some of you asked, do you need it separate? What does it mean? How does it work? And all that kind of stuff. It's really simple. Let's go over it again. Whenever you make a video, whether it's for an in-class exercise or for an assignment, the way it's going to go is this. For the in-class exercise, let's start there. You need a lab report. Assignments, you don't need a lab report, all right? Because the assignment is a little bit more hefty. You already have a bit of an area where all the marks are coming from, and I've already told you a couple of things about details about what you want to put together. So there's no lab report required for the assignment. However, for in-class exercises, you need to fill out your lab report, and most of you have done that. I've looked over the stuff that you've submitted. Most of you have done that very well. You've said, yes, I've done it, or I haven't done it, or whatever. This is good. The other thing is a GitHub link. So you need a GitHub link. GitHub is the way for me to check the code, and see that you've done what I've asked you to do, look at your assignment and all that kind of stuff if I need to go into details. However, I want you to demo the stuff that I've asked you to do in your in-class exercises live in some kind of video. Now, I prefer YouTube, but you can use any other clickable streaming provider. Click on it, I run the video. That you have your choice. That's how it's going to be. In the video, you need a single slide, could even be Word page, that is like a title card to show your face and an image of you, actually. And it basically says, hi, my name is, and this is the video for in-class exercise, blah, right? Or when you're doing your assignment, this is the same thing. Hi, my name is, and this is the video for my assignment number, blah, whatever it's going to be, right? And you quickly get into the details for your in-class exercise or your assignment. For in-class exercises, there are going to be a series of tasks that I put together inside of your lab report, and I want you to show your lab report in your video. That's what it's going to be. So your video is going to show your lab report and what you've completed and what you couldn't get done. If you couldn't get something done, show it and say, look, I've got all these parts done, but I didn't do this part. Let me demonstrate these things for you. Hi, look, here's my GitHub repo. Yes, excellent. Here is this thing that you've asked me to do. Here's the other thing. I don't need you to talk code. So I don't need you to go through your code and go, you can see here that the for loop. No, just show me what I'm looking for in terms of your functionality. If there's a piece of code that I've asked you to describe, because let's say, for example, we're doing a special algorithm, show me the code and talk about how this works. Not code by line. I never want you to recite code line by line. It's useless for me, and it's absolutely useless for you, probably boring too. So please don't do that. Talk about it. Then move on to the next task, the next task, and the next task as quickly as you can within reason until it's about 1 to 3 minutes for your in-class exercise. Something small, very, very simple. How do you record your video? Some people have been having trouble with that. One way to record video is to use OBS, right? And you download that free software that allows you to record your screen. That's all I need you to do. And your voice. I need to hear you speak, right? Because I need to hear that you understand, not some robot voice, not somebody else's voice. It's got to be your voice. Okay. So just being very clear there. I've heard over the years many different things. Okay. Just many different submissions with a lot of creativity sometimes too. But it's got to be your voice. Okay, so it's got to be your voice. You got to talk about it. I got to see your screen. I got to, hear what you're saying. You need to explain stuff. Stick to the basics. I don't need music in the video. Okay, you don't have to make it like, the production values don't have to be high in terms of like, post-production. I don't expect you to make money from the video. I don't need like lower thirds or something weird. Just do the video that you have to do, and it's really just for academic purposes, so I can see that you know what you're doing. That's what it's about. All right. It's the same thing for your assignments, but there's no lab report. You're not going to show a lab report, but you're going to demo the assignment in all of its parts. So here, as an example, let's talk about this assignment. The way you would be doing it is you start off with your card class, because that's what I've asked you to do. So since the card class is the first thing that I've asked you, show me your card class. Say we developed the card class together during our in-class exercise time. Here's the card class, and here are some of the cards. So show me the cards that are related, how we link the card class to the cards, because we actually added a little script. Talk about that a little bit, and those kind of things, and discuss stuff that you understand in Unity. So I want to know how you, as it's going through your brain, how you are understanding everything. All right. Then go on to the standard deck class, and how a standard deck is kind of a collection of cards, right? That's what we're going to be talking about today more than anything else. And go through demonstrate some of these things. If I want to demonstrate the draw next card method, right, as an example, then talk about how maybe the draw next card method is linked to a button press, or something like that. When I'm dealing a card, dealing the cards, if I deal one card, it kind of pops a card off of the stack. Maybe a stack is a good collection to use, which we're going to talk about today a little bit. And then, go through and play the game and show that the game is working and all that kind of stuff. Say, here's how it goes. Here's the score. Here's this. You can see that the game is working fine. It'll continue to work forever, or you can make it work once. It's up to you. Worst case scenario, And so you talk about those three parts. This could take a little longer because it's a larger thing. So instead of it taking 1 to 3 minutes, it might take 5 to 10 minutes that you're going to talk max. Okay, like again, talk efficiently. I don't need you to recode too much in this case. And internal documentation, I don't need you to go over it, but it has to be there. I will look for it. And then your video is also, you're getting paid in marks for your video too. So even though it's mandatory, you cannot submit anything, no in-class exercise and no assignment without a video. If you submit without a video, I haven't marked your stuff yet, but you're going to see it. It's going to come back to you and it's going to say, please resubmit with a video. That's what it's going to say. Okay, so I need it. It's required, and there's no way around it. For the assignment, you can submit. Worst case, you can submit late. Okay, I don't recommend it. Every day late is minus 20%. Okay, 3 days late, no more submission. That's how we're going to run it for this semester. And the reason for this is I want you guys to be on time reasonably. You've had a couple of weeks, last week for sure. You could have started thinking about how to put this together if you saw the assignment. Hopefully you did. And you still have a week, and I think we're still going to build it out. I don't think there's going to be any reason for you to be late. But if you need to be late and you have some extraneous circumstance that comes up, as an example, then usually I give you 3 days. So if the assignment's due on Sunday, worst case by Wednesday, you must submit by Wednesday at midnight, but you still get minus 60% off your assignment, which is a huge hit, right? Worst case scenario. So please try not to do that. I also don't recommend that you wait until the last minute to submit your stuff. I know some people are into that and you guys have a lot of work that you're doing all at the same time. I recommend targeting, instead of Sunday, target Saturday, right? I know that it's kind of weird and people wait to the last minute because it's, like I said, it's low hanging fruit. What's the easiest stuff to do? If this assignment's worth only 8%, some people will elect not to do it. And a good example of that is only 6 people out of 9, have submitted in-class exercise 1 and in-class exercise 2. That's 8% of your final grade lost for those people who didn't submit for whatever reason, okay? And I can't give you marks for stuff you haven't submitted. So what I'd ask you to do is submit something, even if it's crap, right? I mean, something is usually better than nothing, right? Unless it's like literally nothing that you've submitted. You submitted something that doesn't even have anything. I mean, I can't mark something that isn't there, or it's like completely not going to meet requirements. But if you try and you give me something, right, I will give you some marks for it. Okay. So, so submit often. I'm going to take the latest submission. So if you submit a couple times, the last one is what I'm going to be looking at, not the first one. And so that means that you have a chance to kind of at least get some marks, part marks, worst case scenario, if you don't know how to do something. Although I suspect that you'll be able to do everything just fine if you follow along in class. Okay, so that's kind of how it is. I'm hoping I'm answering your questions when it comes to what I'm expecting. So again, summary again. Things to submit for an in-class exercise: lab report separate, GitHub link, YouTube video, and in the YouTube video link, hopefully it's YouTube video, in the YouTube video, show your lab report, right? That's for your in-class exercise. For assignments, GitHub link, the link to your video. That's it. There's no lab report requirement inside the assignment because it's a more hefty assignment. There's like more things to do, and you're going to talk about it more in your video report more than anything else. Okay, so that is how it is. Any other questions around assignments or in-class exercise requirements?
I've been putting my video links in my lab reports there. Is that fine? Was that put that there, or should I?
You don't need it in your lab report. I mean, do you mean that you didn't show your lab report in your video?
Well, that too, and is that a good place to put the link? Yeah,
I would put it in just when you submit. Like when you submit, you have a submission box, and you have that's you just put the link in somewhere, even if it's in plain text. I can always click onto it, and I can always and make it go as long as I can clearly see the link. So don't zip it up. I'm hoping that you're not going to, kind of do anything like compress it in something. I got to download. I don't want to download anything. I want to be able to go through, click on it, look at it, move on, right? So it should be kind of very.
All right, I'll start doing that instead. Thank you.
No problem. All right. So again, any other questions around in-class exercises or assignments? before we move on today. I wanted to kind of clarify that. I know it's different maybe than some other professors that you're with, but it's going to be better for you for a bunch of reasons. One is when you go through your video, I'm sure you've done videos for other people, you're really, explain, it's going through your brain, right? And you're kind of, it's almost like an oral exam in many ways. Like you're kind of saying, hey, this is what I understand. Here's how and you're talking about code. You're talking about the thing as much as you can, which is really great for you. And because then when you're talking about code and you're talking about your project, even the process of doing that and kind of figuring out what to say is really great for you. And also, video is really great because I can see what you're doing, and it's going to be really quick for me to mark and for you to do. It shouldn't be long. I don't expect you to make it takes take an hour to make a 5-minute video, right? It should be literally without too much, I would say, editing, right? I mean editing as in like redoing your video again. It should be 1 or 2 takes max. Like I don't expect you to be perfect, and even if you mess up and if it doesn't work, just talk through it. Okay, like don't worry about it. Okay, I'm not going to be judgy at all in terms of your production quality, as long as, and here's the proviso: can I see your screen? Can I hear what you're saying? Do I understand what you mean? Good to go. Okay, if I have questions, I will connect with you. All right, like I will send you a note saying I really didn't understand what or I might send you I might connect with you on Discord and say, can you please resubmit, or whatever, something like that. Okay, so any other questions related to the assignment or in-class exercises before we move on?
So just put the links and the submission thing not into the PowerPoint slide, just right in submission.
Yeah, easy.
Okay, cool.
So that way I don't have to open up a PowerPoint, as an example to get to it or whatever. Okay, so that is your assignment 1. I think it's fairly straightforward. And again, we're building it together, so it's not going to be like, too hard. I think as we go forward, assignment 2 will be more challenging. And because some of it we're going to do together and some of it you're going to do completely by yourself, right? Like every other assignment that you'd be doing. I just want to kind of guide you through this first one together. So we build it up, and the in-class exercises are there to help you rebuild some of your capability, I'm going to say, and kind of adhere to the standards that I want you to adhere to. There's GitHub. Maybe some of you haven't really used it to that level. Production, when you're producing your game and stuff like that. How do you do that? How do you target how do you produce different targets, and all that kind of stuff. We've talked about some of those things over the last couple of weeks. Okay, let's move on. So that is the stuff that we were talking about last week, and let's get into this week. So this week's all around sorting algorithms and more about lists. And I'm going to talk about more about lists because we're going to use our lists, to do some sorting and searching and some other things today when it comes to Unity. That's what this week's activity is all about. In-class exercise 3 is due Sunday at midnight. And just a reminder that assignment 1 is due next week, Sunday at midnight. Okay. Let's talk about basic sorting algorithms. So what the heck are they? The 2 main algorithms that are fundamental to everything that we do when it comes to computer science in many ways is sorting and searching. Sorting and searching are the least efficient kinds of algorithms that you can do, right? And the other algorithm that we do a lot is, when we say algorithm, it's just a collection of code, reusable code, usually a function or a couple of functions that work together. Sorting and searching, and a lot of times building. If I want to build something up, if I want to build, like we built our kind of our cards up last time, a list of cards and those kind of things. Any kind of construction is what we do a lot with code. One thing I always ask students when we look at code is, or we're looking at, algorithms is, how do I code this thing, right? So I'm going to be asking that a lot over and over again. So I might ask you something like, oh, we're talking about a graph. How do I code this graph? How do I put this in code? How do I, in your mind, how do I translate it from what you see on paper to what it's going to look like in code? How do we do that, right? And that requires a little bit of problem solving and using some of the tools you know how to use to put things together. So sorting and searching, fundamental. And it's been from the beginning of computers, we've been doing sorting and searching. In fact, if anything, it's kind of the reason why we want sorting and searching is because it's like I want to find something. The big news nowadays is Chat GPT, right? Which is a generative algorithm that allows you to chat with an AI, right? That's the main craze that's out there right now. And Microsoft in the news, Microsoft and Google have been battling it out. Google is now, we have Google Search, and Google Search is something that has been with us, for many years now, like 20 years, and approximately 23 actually. Just at the beginning of our time together with the web, that's how long it's been around. And Microsoft has struggled with their browsers, with Internet Explorer and their searching algorithms and everything else. Bing, the Bing search engine, not a great search engine. Not something that I really depend on. I don't even use Firefox. A lot of times I use Google, and I use Google Search primarily. So browsers and the search engine, which are two different things. But lately, in the last couple of days, they're battling it out now. The AI wars are here, right? And I'm talking about who's going to use AI to enhance their capabilities. It's not necessarily artificial intelligence, but rather intelligence augmentation. How do I augment my intelligence with AI? How do I do that? And the people that are going to win this whole thing are the people that use AI to enhance themselves. Not the AI is going to dominate the world and take over or anything like that. Not anytime soon anyway, but more like we're going to be using AI algorithms, right, to kind of enhance ourselves. And one of this stuff that's coming out with is Chat GPT. As soon as Chat GPT came out, which is the ability for you to pull up information, right, with some kind of intelligent agent. That's what it really is. So again, some kind of searching kind of algorithm in many ways. It's got a search and respond, right? That's what it does. As soon as they came out, red flags went all over the place. Like it was code red. It was like red alert at Google. They were like, holy crap, we have something that is potentially better than our Google search coming out right now. It's a threat. It's almost like we talk about a disruptive technology. This is it, guys. It's coming out right now, at least in this time frame. Maybe in next year, there'll be something else. And every year there's something. Uber was a disruptive technology, right? That came out. Airbnb, destructive and disruptive technology in the hotel industry. Chat GPT is disruptive from a search perspective. It's coming out right now, right? It's out. And Microsoft in recent days, a couple of days now, they had this little, conference, and they basically said, hey, our Edge browser, a replacement for Internet Explorer, which isn't much better in my opinion, right? Our Edge browser, which uses Bing search, we're going to attach a Chat GPT that is connected to the internet, right? And that is way better than Chat GPT from OpenAI. It's better, right? And they knocked it out of the park. If you actually watch the video that they talk about with Microsoft basically says it's integrated into your Edge browser, and you can actually search for a result, and then you can use Chat GPT equivalent, the chat function in your browser with the context of whatever you're searching for, to kind of ask more information and compare two things, look at a PDF. Like they use amazing stuff, and it can really save you time. And so think about this: an advanced searching algorithm that uses AI that's going to clobber Google when it comes to the way they're doing things. Now, I think Google's going to come back with their own stuff because they've basically didn't have anything to kind of combat Microsoft. Their Chat GPT was exactly what it was. There's nothing advanced about it. Microsoft's claiming that their version of Chat is better than Chat GPT. And so that's the things that are happening. And if you don't know what it is, and does anyone not know what I'm talking about? Chat GPT? Anybody? You guys all know. Yay. Okay. Have you tried it? Has anyone tried it at all?
Yeah, a lot of us are using it to be able to help us with our assignments when we're trying to look for troubleshoot through problems and stuff.
Awesome. Okay, great. And so that's also another one. That's why it's another disruptive technology for education, because Imagine if, ChatGPT has been something that has been, they claimed that it can pass a level 3 engineer for Google and makes $100,000 a year. It's got a lot of things there. So imagine intelligence augmentation, which is kind of interesting. So search, it's kind of a really example of an advanced searching algorithm more than anything else. Search and retrieve and respond, basically. So that is something that we're going to be seeing more and more, AI. And not only that, let's take it to the next level. It's going to be used in almost anything. You're writing a paper, or you're an essay or something like that. Imagine Microsoft's going to include that in your Word documentation, right? So all of a sudden it'll kind of make recommendations saying, hey, other people who've written something similar have done this, right? Take a look. Here's some things that they've written. And yours seems to be, we're going to rank you compared to what other people have written, and yours kind of seems to be middling or low in terms of your explanation. We recommend adding these kind of details here. It's going to come, right?
Yeah,
And so
doctors were using it to write notes for their patients and stuff, because I guess there's some format like NHS or something like that, where you can type in the information and then say an NHS style, and it literally fills out an entire chart that they can just copy and paste into their notes.
think about that, right? That time saving, right? And that's where we're going. So intelligence augmentation. Let's go back to AR for a second. Never mind VR. VR was supposed to be the killer app 5 years ago, 10 years ago, actually. VR has been around for a long time. And every time we talk about VR, man, some people are using it, some people won't, some people, there's some good applications, Beat Saber. I mean, and there's some other ones that are out there too. Maybe if you played Arizona Sunshine, is kind of neat in terms of even multiplayer and those kind of things. But there's still never a killer app for VR, not really, right? You don't really need VR in anything. But AR, now there's something. AR, augmented reality, or even a heads-up display. Imagine augmenting our intelligence with a heads-up display that we can see all the time, right? Or taking your screen and freeing the ability, instead of they were talking about the fourth dimension. I'm talking 10 years ago. I was talking about it, where our screens, we're always doing this with our head. We're always looking down at our screen. And one day, like the Neanderthal, we're not going to look down at our screens. We're actually going to look up, and there's going to be something in our eyes that we're going to see, which is a heads-up display, and it's going to enhance our intelligence. Yes, we have intelligence, and we're going to see other things. We're going to get more information. And I'm being very idealistic here. All right, there are some negative things. There's always negative things to any technology, but let's take it positively, right, for a second. One thing that people always, criticize this kind of technology, even ChatGPT and OpenAI, that whole initiative, is it's going to make us stupider. Right? We're going to get stupid because we can just depend on ChatGPT to give us our responses, as opposed to trying to think and problem solve on our own. And I don't think so. I think what it's going to do is going to change some of the questions we're asking. I think that's what it's going to do. Just like people are afraid of visual coding. You guys are doing blueprints with Unreal, right? And those kind of things. And some people are always worried, oh, visual coding is going to be low code, no code revolution. We're not going to code anymore. There's not going to be any need for a developer in the future. I'd call BS on that, right? And I'll say why. It's because sure, you can visually code, but there's going to be something that's going to have to fix your code, right? I mean, if you're, visually coding, and there's a whole art to doing, visual code, any kind of visually coding algorithm, right? And the reason for this is because when I have nodes that I want to link together, whether it's for Blender or whether it's for Unreal or whether it's for whatever, I'm making textures, as an example, it doesn't matter. You need to understand how nodes kind of fit together and how that whole thing works. There's some stuff around it, and someone wrote the code that's underlying for the blueprints, and it's not always perfect, right? So there's going to be always room for us as developers, right, to go in and fix stuff, and it's going to give us other opportunities for artists and for other people to get into the game space, where they can also contribute. And it doesn't have to be a hard low-level developer that does it all, right? Which is pretty cool. So that's kind of my intro. I think, searching and sorting, it's so fundamental, but it's so powerful. If you think about if you can ask for something, the machine gods, You ask for something from them, and all of a sudden it's there. You know, it's kind of an amazing thing that we kind of take for granted. You know, when we look on Google, you guys have access to the biggest library in the world. And when I was growing up, I know I'm sorry, I'm sounding like a dad now, but it is what it is, right? When I was growing up, there was nothing like that. I had no cell phone and there was no fax machines or anything. The web was a dream, right? And we had to go to the library to look up everything. And the library was pretty sparse, right, where I was living. So, you know, you travel far to collect books and all that kind of stuff. And there was a lot more reading involved back then. Now we have everything at our fingertips and just with Google. And just in the near future, we're going to have a lot more information that is going to be available to us through sorting and searching algorithms, and more advanced sorting and searching algorithms. Because if you think about what that AI is, it's not general artificial intelligence. That's like your killer AI, like Terminator. It's artificial intelligence that's been trained, right? That's using a training data set to respond to what you're kind of asking it. You're asking it, it's looking at some of the word choices that you have, looking at intents. That's like your natural language processing. That's part of ChatGPT. And it's returning information from a collection, a database, a trained database from the same kind of searches that other people have done and that you're doing. You're actually training it as you're asking the questions, which is kind of interesting. Anyways, we're kind of getting off topic, but interesting and very, I would say exciting times, scary times too. Okay. So sorting algorithms is the first part. Next week, we're talking about searching algorithms. Let's talk about sorting first. Searching without sorting is very difficult and very inefficient. So this is why we sort first. And so what we want to do, we sort all the time, every day. When if we think about it, if I'm doing things manually, I'm talking about in the real world, the analog world, not the digital world. You know, even when some things that we've seen out there, if I'm online shopping, there's sorting going on all the time. It's sorting by value or cost or whatever. I might order things in the real world by size. Let's say I want to sort my socks. I don't know, when I'm doing my laundry or whatever. I want to sort by size and color and type, right? Those kind of things. Postal service, sorting by mail, inventory management in real life in a warehouse, sorting, you know, your items. Hospital, prioritizing patients based on urgency, which is really like a value, a number. Is it really urgent? Is it not so urgent? How severe is it? Maybe severity and origin and urgency. You can kind of come up with a chart like that. Airport, sorting and delivering luggage. We do it all the time, like in different things. And these are just some examples of how we sort in the real world. So again, we want to think about sorting as a fundamental process that we want to duplicate digitally with computer stuff. All right. So the first one we want to talk about, which is the slowest sorting algorithms, or one of the slowest sorting algorithms, is the bubble sort. Bubble sort is something that's been around for a long time, like before I was a programmer. It's been around that long. And so what is it? It was very basic. And what it does is, the reason why it gets its name bubble sort, it's kind of like the values float like bubbles from one end of the list to the other. That's what the idea is. Okay, if you can abstract, you know, your mind and think about that, think about it that way. When we think about a list of numbers, we think about them in ascending order. Typically, you can also sort in descending order. Ascending order means from lowest to highest, descending order from highest to lowest. But however you sort, whether it's ascending or descending, what you want to do in this algorithm, what it does is it goes through the list many times. Okay, remember that when we talked about big O notation, day one, we talked about how many times we loop through something, right? If I loop through a list one time, it's O to the n, which means time complexity. We're going to, for every n number of items, if I have 10 items, I'm going to do that iteration 10 times, O to the n. That's what that means. Here, I'm looping through the same list of items many times, which means it cannot be just O to the n. If you think about it, it's not a straight algorithm. O to the n is not a bad, it's pretty good in terms of efficiency. We're not doing O to the n here, okay? And we'll talk about what that time space complexity thing is going to look like later on, okay? So the way it works is we have, let's suppose I have two numbers, 2 and 72. Here's 2 and 72, and they're highlighted in these circles. And 72 moves from the beginning of the array, again, to kind of in the middle of the array, right? That's where it's going to move to. right? And 2 moves from just past the middle all the way to the beginning of the array. And the way it works is we kind of loop through kind of the items in the array and start comparing the current item with the next item. So it kind of moves from one step to the other, it kind of moves toward the right. So I take the first item as an example with my looping, and I go, okay, is 72 less than 54? No, swap. Is 72 less than 59? No, swap. Is 72 less than 30? No, swap. And it keeps doing that until it gets to this. And then is 72 less than 2? No, swap. So it's here now. Is 72 less than 72? No, stop. Okay, so it's the same, because now it's 72 and 72 are equal, so that moving 72, the value of 72, it kind of moves to there and stops moving, because you can't go on. If 72 is already less than 72, that's the thing. So now I keep going to the next number. Okay, 54 less than 59, yes. So leave it where it is, right? We don't move 54 because 54 is less than 59, as an example, right? And we go to 59. And we keep doing this throughout the list, and we keep going in several iterations until the list, you can see, is starting to change shape. It's starting to change in terms of order. And finally, we get to something that looks like this, okay? Where 2 is the least, the lowest value, and 82 is the highest value. And so we keep on, we have some kind of swapping method that we use when we swap numbers out. The code for it looks like this, okay? And again, I don't want to go through code too much without doing it, but I want to mention a couple things here. So a double for loop, one that starts at the end and decrements. So it kind of starts at the end of the loop and goes back down, 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 down. And one that starts at the beginning of the loop and goes up, 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 up. So they go, the 2 loops kind of go in the opposite directions. And what this does for us is whenever we think about a for loop, a double for loop, it cannot be O of n anymore, because we have a for loop inside of another for loop. There's time for these 2 things. And typically when we have those, one for loop and another for loop, right there, it's like n squared. Okay, right there. Whenever we have a for loop and a for loop, typically it's n squared in terms of its quadratic time. Okay. And this even makes it more complex. This is the swapping algorithm. So I have a temporary variable. I assign some value to the temporary variable, whatever the thing I want to swap. Let's suppose back over here, I want to swap the 72 and the 54. I have a temporary variable that I assign, as an example, 72. I take 72 and assign it to that temporary variable. And then I swap where whatever 72 was being held, I swap that location. I take 54 and I put it into 72, and then I take 72 and I put it where 54 was, right? And I do that by this swapping. So temp is equal to whatever the previous was, and then I say previous is equal to the new one, and then I say the new one is now equal to temp, right? And that's how it works. That's kind of your swapping algorithm right here. This is the heart of the bubble sort, the swap, okay? And you're going to see that the swap, this little swap algorithm, is something that's going to be repeated in the other sorting algorithms that we're going to be talking about. So again, the heart of the bubble sort is the swapping algorithm. And here's another example. I have it does several passes. Okay, so we start off with something like an array like 7, 6, 4, 3, and then again we start comparing. Is 7 less than 6? No, swap. Is 7 less than 4? No, swap. Is 7 less than 3? No, swap. And so we have the first iteration of our first pass that looks like this: 6, 4, 3, 7, right? Because we've just gone through the list one time. And then I go through it again. I start with the first part again. So by now I'm into this a smaller part of the list because I've already handled 7. 7's already bubbled to the right, as an example. So I'm going to go, okay, 6 less than 4? No. And then swap and keep doing that until 6 is where it's supposed to be. And then I start with 4. And this is the worst case scenario that we're seeing here, because it's 7, 6, 4, 3. So it's descending order, and I'm going to change it to ascending order. That is the worst case scenario for this kind of sorting algorithm, because that means I have to sort every single element in the array, as an example, or list, to opposite of what it is right now. That is the worst case scenario. Okay. And when it comes to algorithms like this, there's best case. Best case scenario would be already sorted, right? So it's already sorted. It's random, but it could be. a fully already sorted array, well, there's nothing to do. We just look through everything and you're done, right? As an example, that's the best case scenario. So that would be like O of n, right? Which is just linear again. So I'm looping through each element. Well, they're already in sorted order. I'm good to go, right? That's the best case scenario. Worst case scenario is it's reverse, and now I have to do every single element, and the average here is O, n squared, which again is quadratic. Okay, so that's how it works. So that's bubble sort in a nutshell. We have two loops, the outer loop and the inner loop, and I talked about what they do. Let's move on to the next sorting algorithm. And again, I don't want to go into too much detail here because I know that traditionally lectures theory is bad. We want to practice some of this stuff too, right? Sorting. So how do we do the selection sort? Selection sort is a different philosophy a little bit in terms of the way it works. So again, it works by starting at the beginning of the array, comparing the first element with all the other elements in the array, and then selecting the smallest element and putting it at the beginning. That's the first thing we do. The first part is find the smallest element in the array. So here we loop through, we loop through, we loop through, we find 2. Hey, 2 is the smallest element. Let's put it right here, all right? And the way that would be done is if there's something else right here that is bigger, example 72, we swap. Okay, that's what the first thing that's been done. Next, we take the next element and we go, okay, let's take a look at find the next smallest element in the array. Okay, so again, I go through the next smallest element and I find 30, and I say, well, 30 is the next smallest element, and I need to put it next to 2. So then I take 30 and I swap it out with 54. Swap, right? Swaps again. So now 30 is here and 54 is there. Then I look at the next smallest element. So I loop through the whole thing, blah, 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 blah. Find the next smallest element, which is 31. 31 is the next smallest element. I put it in this third place, right? And then whatever was in there before, I swap with 31. And then I keep looking through the next one and the next one, and I keep doing that until the entire array is sorted. Now, this is a longer algorithm. And it's actually, in many ways, you might say it's worse in some ways, selection sort. But actually, it depends on the number of iterations. In the beginning, for small amounts of numbers, bubble sort and selection sort are almost identical in terms of the number of the time complexity. It takes them about the same amount of time. But as we increase the number of elements that we go through, actually selection sort is slightly more efficient than, I would say much more efficient than bubble sort. Bubble sort is really bad, right? Especially for larger data sets, bubble sort is pretty bad, but selection sort is better, right? And it may not look like it in the beginning because, we're kind of looking for that smallest element. We're looking through the list every single time. I'm looping through the entire list. I'm doing like an O of n through the entire list to find that smallest element again from the remaining elements. Okay, so again, I don't look through, when I look through the smallest element, I forget about the first position. So think about this as if I start, kind of over here, right? I found 2 and I swap it out with 72. That's okay. But now I forgot about this position. So this position is done. I've done this position. That's what I'm doing, right? I don't think about this anymore. When I look through the next part of the selection sort, I'm just looking from here all the way to here. That's what I'm caring about now, all right? And when I find 30, well, now this is done. And I keep on scratching out each one of these things. And so my list becomes smaller and smaller. The list that I'm looking for, the smallest number, becomes smaller and smaller. So then it becomes quicker and quicker for me to be able to do that swapping. So in larger data sets, that's where we can kind of profit from this kind of approach because, we're kind of getting smaller and smaller. Whereas in the previous example, bubble sort always uses the same amount of time to do everything. And so that it's always going to be bad, right? Easy, but bad. So that is the selection sort, which is kind of better to do stuff with 2 loops that is running, the outer loop and the inner loop. And after each iteration, the inner loop, the most minimum value in the array is assigned to its proper place in the array, which is the beginning, okay? The selection sort code looks like this, and you can see we have the exact same swapping algorithm right here. One thing that you might say to yourself is, why not make this swap into a function? Well, the function call itself has cost. If I make a function call, I'm calling that function. And if I'm calling it many times, as an example, and if it's only 3 lines of code, it makes sense to keep my function actually here, as opposed to like my little lines of code here, 1, 2, 3 lines of code. Keep it here because we're calling it a bunch of times, right? If I'm calling something like once or a smaller amount of time, or if the amount of code that I'm calling is large, function call, right? Because that makes sense. Okay, go here, do this little thing, come back, right? But in the process of going there and coming back, that costs time, because remember how functions work. And if you don't know how functions work, they work like this. As soon as I call that function, it's a subroutine. That's what a subroutine is. So it's function, right? And machine code, the way it works is when I call the function, it goes on something called stack, right? And so then that function is being called, and that is a copy of the function is put on the stack, and that's the one that we're going to. When the function resolves, the function itself is popped off the stack, and we go back to the previous wherever we called the function from, the calling area, the calling place, if you will, right? So it goes back to where we were before, right? But first it's got to do this over here, this magic over here, and then go back, right? That going over here and coming back takes time, even a little time, doesn't matter, right? And if I do this all over the time, if I keep doing this over and over again, because I'm iterating, I don't know, 1,000 times or 10,000 times, that's an extra overhead that I don't need, as opposed to, well, here's my function and I just do it over here. I'm not moving from here to here. I'm just doing it in this little area here, right? So that's why it makes sense, especially when it comes to sorting and searching algorithms, that we have our little swapping to be happening right here. If you see it in other places, some people may code it because they're like, well, this is being repeated. If it's something I'm using in like different kinds of sorts, maybe I might make it a function, but it's gonna be less efficient unless I do it like this. All right. So there's 2 sorts. They're kind of almost the same in terms of using an inner loop and an outer loop. And then we come to insertion sort. And every time we do an insertion, if you think about just the name insertion sort, right, we know it's less efficient in general than the other sorting functions. Again, it works similar in many ways to having a group of playing cards in your hands, right? That's how it works. So the array is split into sorted and unsorted piles. I got my sorted part and I got my unsorted part. And what I want to do is I want to insert the card where it's supposed to go in the sorted part. Okay, that's how it works. Okay, so it looks a little different. And it also works a little different. Take a look at the swapping algorithm here, right? Forget the actual code, what it actually looks like. Just look at the shape of the code here for yourself. And if you look at the shape of the code, you can clearly see there's an issue here, right? Compared to what it looks like. My swap requires a while loop, okay? So I'm swapping a bunch of times, not just one time. And I'm swapping a bunch of times for each iteration of my outer loop, right? So my inner loop is a while loop that's going to swap. Whereas the other way that we did it was, and by the way, it's not just a swapping, but an assignment. So here part of the swapping is happening here, right? Where I make temp. Here's my temp. I make a temp variable, and it kind of looks at my previous, whatever my previous thing that I'm going to swap out. And then, I do some part of my swap here, and then some part of my swap outside the loop. Overall, the insertion sort is the least efficient algorithm, out of the 3 when it comes to larger data sets, right? For sure. Smaller data sets, it's slightly less efficient than its other 2, right? But it's comparable, okay, for smaller data sets. Larger data sets, this is bad. This is really bad. Worse than bubble sort and way worse than selection sort, okay? So that's how it is in terms of the way it is. Neat, again, in terms of the way it's laid out, because, again, if you think about this, it starts at the beginning. So where order is 1, the outer is 1, starts off at the second, position, if you will, and it keeps looping until, it gets to the end. And then the swapping happens immediately. Like, we're not even checking. We're saying get temporary, get whatever this current index is, kind of save that current index. And then basically this while loop says, while the inner value, which is equal to the outer value, whatever that outer, think about row column. I'm always thinking about rows and columns. I take that number one, let's say if, index 1 is greater than 0, right? So if this is not 0, then what I'm going to do is I'm going to subtract. This goes the other way. So it kind of goes from the end back to the middle. The inner one goes from the end to the middle, and the outer one goes from the start to the end, as an example, or the end to the start, right, for this one. So it's kind of different written, and it's harder to read when you look at it. When you look at trying to figure out, whenever I want you to always do a code reading exercise, if you ever do that, you look at this one, you're like, this one doesn't make as much sense. It's like, I need to think about this a little bit more compared to these ones, which is, okay, I've got my for loop, I got another for loop, and inside there I do a swap. Okay, I can see that there's a selection. I'm selecting which one is minimum. That's what I'm doing with the selection sort for the most times, right? And that's all I'm doing as I'm looping through each of the elements. But notice my swap is only happening on the outside loop, right? Not within this for loop somehow. Whereas you can clearly see that part of the swap is happening within the loop. Bad, right? And even the bubble sort, if I go back up, you can see that the bubble sort is also bad in that way because the entire swap is happening within the loop, right? So you might say, well, shouldn't the bubble sort be worse? Actually, it's because of the complexity of the code. It's very, very simple, right? And the complexity of the code, because it's simple, makes it more efficient than the actual the insertion sort. All right, so that's kind of how it works. So so interesting the way it works, and it has two loops. The outer loop moves from the element by element through the array, whereas the inner loop compares the element chosen in the outer loop to the element next to it in the array, and that's when we do our swapping. Let's do some analysis. Bubble sort, like we said before, right? Best case scenario is a sorted array, O of n. So linear time, right? And worst case scenario, a reversed sorted array with very few elements or very few elements are in proper place, O of n squared, which is again, quadratic time, right? The average case is O to the n squared, which is pretty bad, right? In terms of the way it works. Advantage, simplest sorting approach, easy to implement. Best case complexity of O to the n, which means there is a best case. Stable sort does not change relative order. We can do an in-place sort where I don't need to have two different data structures. I have one data structure here, another data structure here, and I do some weird swapping with the data structures. I can just do it in one data structure in place, which is pretty cool. Disadvantage, comparatively slower, poor efficiency for larger elements, large elements of array. Okay. Selection sort. Best case O to the n squared, worst case O to the n squared with a reversely sorted thing. So best case and worst case is the same, right? Advantage, it can also be used on list structures. That's really cool, which is great. We can add and remove efficient things. The number of swaps is reduced. O to the n swaps in all cases, which is better than what we had when it came to, remember, because we are swapping, like we talked about. If you look at the swapping part, it's outside of the second loop, right? Whereas the bubble sort has the swapping inside the second loop, right? So that's swapping many, many more times, right? As this one only swaps sometimes, depending on if the minimum value, is the one we need to swap. If not, we don't swap every single time, right? Which is pretty cool. So that is the advantage of selection sort. It doesn't always swap. It only swaps the minimum. It's an in-place sort, so we don't have two data structures. Disadvantage, time complexity in all cases is O to the n squared. So there is no best case scenario for this thing. Best case, worst case, average case, all the same, right? And it requires n squared number of steps for sorting n elements, and it is not scalable, which means, very large, very, very large data sets, bad, right? So that's how it works. Analysis of insertion sort. Again, best case scenario, a sorted array as input, it's O to the n, so it's good in terms of, because it's already been done. Reversely sorted, O to the n squared, again, it looks the same, but if you actually, so advantage, it can be easily computed. Best case complexity, O to the n, number of swaps reduced in the bubble sort, it is reduced because we've taken some of those pieces that have been removed out of that second loop. It's a stable sort, it's adaptive. So total number of steps is reduced for partially sorted array. Yes, this is good. It's an in-place sort. Disadvantage is generally used when the value of n is small. For larger values of n, that means larger data sets, it is completely inefficient. So like 1,000 elements compared to 10 elements, it's like the worst one of them, right? So for smaller cases, not a bad idea to use an insertion sort. Larger cases, forget about it, okay? And we look at it from a chart perspective, you can see, time, complexity, best, averaging, worst case. Bonus, let's talk about bonus. Merge sort. Now this is an advanced sorting algorithm, and I want to talk about the advanced sorting algorithm just in a second. And I'm saying it's a bonus because, we're supposed to be talking about basic sorting algorithms today, but I want to talk about merge because merge helps us build other more complex algorithms later on. We're also going to be talking about quick sort and a bunch of other sorting algorithms in the advanced. This is one of the advanced algorithms that I want to talk about a little bit because we also use recursion here, which is kind of a link to the topic for next week. Okay, let's talk about this. So again, it's the way it works is it creates two subarrays. Okay, so now it's not an in-place kind of sorting algorithm. Okay, in-place means I don't need to have additional collections. I just have one collection and I can do everything with one collection, an in-place kind of situation. So here's the example. So I have 4, 2, 6, 0. I split my array into two subarrays, and now I have 4 and 2. I split this part into two subarrays. Okay, and now I compare the two on the left. I say which one's smaller, 2 or 4? I get into it when I get to this level here. It's very easy for me to compare elements. I start comparing them almost like I decompose all the elements into its like each leaf, if you will, in this whole tree structure. And then what I do is that's when I do the swap. I kind of say, okay, I want to create a new array, which is sorted. So that's 2 and 4. So I take these two elements, like the components, and then I put them into a brand new array that's 2 and 4. And I do the same thing for the other side. I kind of take 6 and 0, split them up, right, as an example. And then I say, okay, which one is smaller? 0. Okay, put that into a brand new array that is 0 and 6. Okay, and then I take these two and I say, okay, cool. Now that I have these two arrays, well, now we're going to sort it into something that looks like this. And this step from here to here, there's a couple of additional things that this is not showing, but for the most part, that is what we do. We kind of split it up, and it's almost like a divide and conquer approach that we use with merge sort. Okay, we divide the array, sort each half, and then merge the halves back together. That's the merge part. Right, and the merge part actually has sorting, some kind of sorting and swapping as well inside of it. Okay, popular choice for sorting large data sets because it's relatively efficient and easy to implement. And let me just put easy in quotations, okay, because you're going to see the code here compared to the other ones. Okay, and I just want you to look at the shape. Okay, again, I'm not looking at code and every line of code. I'm not looking at that with you guys right now. What I want you just to feel for yourself when you look at code is, holy crap, what's happening here, right? So let's take a look at the code. So here's how it starts. We have our merge algorithm, and the merge function itself takes in a array of integers, right? That's the first part, the temp array. And then we have kind of our low point or the low part and the high part, and then kind of an upper bound that we use, right? And we kind of say that the lower bound is equal to the low number, whatever the low one is in that part. So these numbers are given. This number here and this number here is kind of sent into the merge function. Okay, that's one thing to note, right? And then we have these numbers. What's the low number and what's the high number? We kind of have that, right? And then it does a while loop, and the while loop compares, where we have the midpoint is equal to the high point minus 1. And then we kind of do some comparisons where we do a while loop here, and then we do another while loop and another while loop, right? Easy to implement. A while loop, another while loop, here's another, here, and there's a for loop at the end. And you can see that it does its magic as an example. And one thing to note is it doesn't return anything. It returns void, which means all the work is being done as a reference, because when we pass an array into a function in C#, remember that we're passing by reference. We're not passing by value. We're not making a copy of the array. We're passing a pointer to the array in C#. in the signature of the method. That's what happens. Okay. So forget what it looks like. This is easy, right? When you look at it. And you know what? Off the top of your head, you probably can't construct something like this from nowhere. You have to kind of look it up, try to figure out how someone constructed this merge sort. And by the way, this is only one part of the whole merge sort thing. This is just the merge function, how you merge. This is the merge part. This is that last part that does this last step. That's what this is, okay? And then we actually have down here the merge sort function. And the merge sort function, what it does is it has my integer array, which is the temp array, and which is an integer array of whatever number of elements, 30 elements, 50 elements, 1,000 elements, 10,000 elements. And then I call something called recursive merge sort. So merge sort calls the recursive piece, recursive merge sort, where I pass in the temporary array, the starting location, which is the left boundary. This is actually left bound, is what it should be, left bound. The left boundary is it starts at 0, and it goes, the upper bound goes at the number of elements minus 1. So a number of elements, let's say if I did 10 elements total, then this would be 10 minus 1, which is 9. So it goes from 0 to 9. It's just the bounds of the array. So the array, the lower bound, and the upper bound, and I pass that into this thing called recursive. That's what rec means, recursive merge sort. If my lower bound is equal to my upper bound, so let's say, for example, the lower bound is 0 and the upper bound is 0, then return. So don't even do anything, okay? Because this is kind of a little case where it's possible that you might, send in, one element of an array. We don't need to do anything if it's only one element. Don't do recursive anything if you only have one element in the array. It's possible, right? Okay, so that's one thing. And then else, if it's not one element of the array, then we can say that the midpoint for the array is the left bound plus the upper bound. These are the indices. So for example, if I go from 0 to 10, 0 to 9, sorry, then I take 0 plus 9 divided by 2, and it's going to give you an integer value. So that means that it'll be like 9 divided by 2 is like 4.5. It'll drop off the 0.5. It'll make it 4, right? So then midpoint is a 4. So from 0 to 9, the midpoint is 4. So it goes 0, 1, 2, 3, 4, which is actually the fifth element. Okay, that's how it works, right? Because the array is 0 base counting. Cool. So that's the midpoint. So it finds the midpoint for you. And then what it passes into the recursive merge sort. Wait, what? The recursive merge sort, right? Is it actually passes in this. It goes, well, look, I'm going to pass this back into the recursive merge sort. I'm calling the recursive merge sort from itself. All right, this is how it works. Okay, so I pass it back in here. And then when I do that every single time, as an example, I pass in the temporary array, which is again, this part, right? So this is the array itself, the left bound in the midpoint. So now when I come back in here, the left bound is the left bound and the upper bound is the midpoint. That's the next recursive call, right? And then I come back and check to see if these are not the case. And if it's not the case, then I go back and calculate a new midpoint. So what is the midpoint? So now you see what I'm doing is I'm going from 0 to 4, where 4 would be the upper bound. That's the midpoint, right? That's what's coming in here. The midpoint is the upper bound, and I'm going 0 to 4, and I add them together and divide by 2. So now it's 2. So that's the midpoint. And then I come back to here and I call myself again, and I keep calling myself again over and over again until I've gotten to that one point, which is 0. I start off at 0. And so I've kind of decoupled all those things together. And then I resolve everything. And this is the base case right here. This is the way to break out of the recursive call, right? Because when I come down to here, I'm going to come to the point where my left bound and my midpoint are the same, 0, right? 0 and 0. And then when that's true, I'm going to return. I'm going to come back to the next layer over here, right? I'm going to come back for the first time. And then when I come back out, it's going to be 0 and 1 as an example. And then I'm going to resolve that one. And I'm going to come back out and it's going to be the other side. So what I've done is slowly, I've decomposed the array into individual components. That's what I'm doing here, right? And that's what I'm doing. I'm kind of going back lower and lower until there's no more. And that's what recursive merge sorting does, okay? And notice that, again, you don't return anything, but what you're doing is you're playing with the original array over and over again. The temp array becomes something that we're looking at. And this is how recursiveness works, okay? Now, this is not a complete algorithm. There's more, okay? But I'm just trying to get you to give you a sense of how this kind of stuff works. Time space complexity for merge sort at the end after you've created your easy implementation, right, is O(n) log n. And we remember we looked at it a couple weeks ago. O(n) to log n is actually a more efficient algorithm than O to the n, right? Which means it's not linear, it's logarithmic. Logarithmic time is actually better than linear time. So where linear time looks like this, it looks like 45-degree, kind of like angle. This is like way down here. It's logarithmic time, right? It's closer to O to the 1, actually, which is way more efficient. And the way this works is because, of the way that it splits things up and takes a look at it. It sounds like it's more complex in terms of the time complexity is more. But because it's using a recursive algorithm and it's decomposing everything into its smaller bits and pieces, later on, and actually for large data sets, it's really efficient, right? So advantages, a good time space complexity, good for large data sets. Merge sort is a stable sort, which means we don't modify the original. We have one, kind of thing. It is easy to implement, like what it says. I'm not sure how easy this would be, but it is easier. I mean, it's one piece of code. It's useful for external sorting. Merge sort algorithm can be easily parallelized, which means it can take advantage of multiple processors because I can take pieces of it. Remember, there's like 3 functions that I'm using here, and I can assign those 3 functions to different places, especially in the recursive side. Every time I have a recursive call, I do a recursive call. I pass that, that new call to another core, and I get that core to work on that recursive part, and I get this other one to work on that recursive part until it comes back and merges in together. Disadvantages, slower compared to other sort algorithms for smaller tasks. But this makes sense because take a look at all those things I have to do. For a small data set that's up to 10 characters, you might use selection sort, or something else, or quick sort. We're going to learn about that later, right? And the other part is we're breaking things down into subarrays, which means we're not using an in-place kind of algorithm, right? So I wanted to compare these two things. I wanted to show you some simple things, maybe that are less efficient, and some more complex things that are more efficient, but more complex to implement, okay? Thoughts, questions, comments on the sorting stuff? Easy to understand, difficult to understand? Does it make sense? What are your thoughts, guys? I know it's not the most exciting topic, but it's a topic you need to understand when it comes to the fundamentals of how things are working for sorting. Any thoughts? No thoughts? That's okay. Let's move on. I'm going to stop recording this piece because we've talked about assignments, right? We've talked about basic sorting algorithms that we might get into, today and so on. And I want to get into the actual in-class exercise, the fun part, which is actually the hands-on stuff that we're doing. So let's stop recording this and get right into the Unity part.